Hi, everybody. Thank you for inviting me. My name is Jennifer. I'm currently pursuing a master's degree in computer science at ASU. I also partner with Hughes Kinetics, and my team and I at the Human Machine Research Lab, we focus on AI driven solutions that target social issues. So, for today, I'll be talking about the quirky world of generative adversary networks. So my objectives is to introduce you to GANs, right? So if you're hearing about GANs for the first time, we'll look at what GANs are, the underlying concepts that GANs are built on. Also, we'll look at some real world examples, what researchers are already doing out there using GANs, right? We'll also see what startup and businesses that are already pushing GANs into production. They're already pushing out features that are built on GANs as well. All right. Okay, before we dive deeper into GANs, I'd like to set the background and talk about neural networks because without neural networks, we won't have GANs, right? And the artificial neural networks is largely inspired by the biological neurons in the human brain. So, neurons largely contribute to our cognitive abilities as humans, right? So, looking at the diagram of a biological neuron, it has this finger like structure called the dendrites, right? And the axons. So the dendrite of a particular neuron connects to the axon of another neuron. All right. And this means that these neurons are all fully connected. And on average, humans have about 80 to 100 billion neurons in the human brain, right? So um, let me give you an example now. So let's say you're having a conversation with a friend, right? And the friend is doing the talking and you're listening. The person doing the talking is generating sound waves, right? So your outer ear, which is the pinna, gathers those sound waves, right? Sends it down to the ear canal, down to the eardrums. The sound wave causes the eardrum to vibrate, which sets the three tiny bones in the middle of the ear into motion, right? So those motions of the bone causes the fluid in the inner ear to move. The movement of those fluid will cause the hair cells to bend, right? The hair cells will change movement into electrical pulses. Those electrical pulses will now be transmitted up to the brain, right? And those electrical pulses are transmitted by they are transmitted by auditory neurons responsible for carrying those sensory information to the brain, right? So that's how important neurons are to the human body, right? So aside auditory neurons, you have neurons in charge of sight and some other abilities for humans as well. Okay, so moving forward, okay, so this is a single neural network called a perceptron, right? So this is like a neural network in its simplest form, right? Okay, so neural networks are made up of layers of neurons, right? Or we can call them nodes. So they're made up of layers of neurons. Right here we have the input layer, right? So the input layer receives input. So your input can be images or data points, any kind of input, right? And here we have the output layer, right? So the output layer produces some kind of result or prediction that we're looking for, right? So input layer takes in input. In between the input layer and the output layer is the hidden layers. So this is where most computation in the network is being done, all right? Inputs are multiplied by a numeric generated value called weight, and their sum is sent as an input to the hidden layer. So we have another numeric value called bias that is also added to the sum, right? So these values, that's the input multiplied by the weight plus the bias, is passed through some kind of a threshold function called the activation function. right? And what this attribution function, what it does for us is that it helps us determine which neuron or which node will get activated or not, all right? So the node or the neuron that is being activated will transfer data to the next, transfer data to the neuron of the next layer, all right? So by the time this all passes through the hidden layers and gets to the output layer, the node with the highest value, right? And the reason why we take highest value is it's a probability between 0 and 1, right? So the node with the highest probability value, the highest value, is being fired up, and that's the node that determines the output, right? So what this means is that this is called forward propagation, because everything goes in from the input layer, information is being passed down through the hidden layers, we get prediction values or results at the output layer, right? This is not all about neural networks, right? So in the training process, right, the predicted output that we get is being compared with the actual or expected output, right? It's being compared with the ground truth, right? So after the comparison, we measure the error. That's how far we are from the actual prediction. So we measure what we have predicted, right, and what is the expected result, right? So after we get our error rates and all the measurements, we send all those information back again to the network and adjust the weights. All right. So all sending it back again to the network is called back propagation. All right. So remember, your input value doesn't change, because your input value could be data points or matrices from an image or whatever your inputs are, right? So the numeric value that you have in your network that changes all the time is weight, right? So by the time you get to the output layer and the result you have, it's very far from the expected result, right? You go back again to the network, change your weight value, and go through the whole process of passing data from one layer to the other. We continue this back and forth, adjusting the weight value until we start getting predictions or results that are close to what we're looking for. Let's go further deep into generative adversarial network. GANs fall under generative models, right? So with a little background in machine learning or science generally, we have discriminative and generative algorithms, or discriminative and generative models, right? Discriminative algorithms don't care much about how data is generated, okay? They just want to perform some magic on your data, categorize your data, that sort of thing. But generative algorithms always go the extra mile to model how data is generated. So given a training data set, right? For example, now, let's say a data set of pictures, photographs, right? So a discriminative algorithm will just focus on, learning to categorize the data in the data set, all right? So differentiating something like cats versus dogs, right? Is this bird? Is this a cat? Is this a dog? Just categorizing the data and performing other sort of tasks on the data, right? But a generative model like GAN, for example, will learn to generate a fresh new data by itself, right? With the same statistics as the training data set. So how GANs achieve this is by using two neural networks, a generator and a discriminator. Okay, so this neural network will be in competition with each other, thus the name adversarial, right? So they're always in the competition with each other. So we're going to call the first neural network, that's the generator, we'll call him SpongeBob, right? And the second one is Squidward. So the discriminator is Squidward. The job of a generator, right, is to generate new data, and the job of the discriminator is to differentiate what's real and what's fake. Okay. So remember, SpongeBob is the generator, right? So Mr. Krabs, who in quote is the AI engineer here now, right? Um, gave SpongeBob a task to produce a golden burger, okay? And Squidward would supervise the cooking. And and the twist here is that SpongeBob doesn't have a template or a cookbook to learn how to produce Mr. Krabs' golden burger. So he's going to learn to generate this new burger by himself, and he has to taste exactly like Mr. Krabs' golden burger, and he has never done it before, and he doesn't have a template, he doesn't have a cookbook, right? And Squidward, the supervisor here, which is the discriminator, would supervise SpongeBob's cooking. All right. So also Squidward also doesn't know how to produce Mr. Krabs' golden burger. He's never done it before, right? So the first thing Squidward does is to learn to differentiate what the fake and the real burger looks like. All right. So he can be this perfect classification model, right? Anytime you throw him a burger that doesn't look like the golden burger, he can always tell you the difference. All right. And Squidward's job is to make sure that um, any burger that SpongeBob spawns out and throws at him, he can always tell whether it's Mr. Krabs' original golden burger or it's just a bunch of fake burger by SpongeBob, right? So the first thing, at first, SpongeBob starts, um, trying to make his burger. He's never done it before. He doesn't have a cookbook. He doesn't have a list. He doesn't have a template. It's just empty-headed neural network, right? So at first, it's going to obviously make something awful because he doesn't have a template, right? So it's going to make a mess and send it to Squidward for approval and say, "Oh, I've made Mr. Krabs' golden burger. I think you should take a look and have a taste," right? So Squidward checks the awful burger and he's good. He's a perfect classification model. I was like, "Oh man, no, this doesn't look like Mr. Krabs' burger. I'm sorry, this tastes awful. It tastes like socks, right? You should take it back and try again." But Squidward also provides SpongeBob some kind of feedback, right? So SpongeBob takes the feedback and tries to improve his cooking. All right. So there's always this back and forth, back and forth, back and forth. So SpongeBob's job is to make sure that his burger is something close to the golden burger, even though he doesn't know how to do it. He just keeps trying different things, but with reference to the feedback that he's also getting from Squidward, right? And Squidward is a somehow perfect classification model that can always sieve out the nonsense burger that SpongeBob is throwing at him and the good, perfect looking golden burger from Mr. Krabs. All right. So at the end of the day, after the whole back and forth, SpongeBob learning from his mistake, picking up the feedback, somehow he learns. He gets so good at um, making this golden burger, all right, that he can even do it with his eyes closed, right? So at the point that Squidward can no longer differentiate the difference between the burger from SpongeBob and the original statistics or the original knowledge he has about the perfect golden burger, at that point, Squidward is defeated. All right. So that means that the generator gets so good at generating a new burger or generating a new data set. So this is what it looks like, right? So here we see the generator producing fake burger, right? So trying to produce something that looks like the original burger, right? And this discriminator beforehand is already trained with some training data set of burgers, right? So it learns to classify between real and fake, okay? and the generator's job is to keep changing its parameters, keep alternating to ensure that it produces a bugger that the discriminator will no longer be able to categorize as fake, right? Looking at some examples, we start with the StyleGAN. StyleGAN was introduced by NVIDIA, right, in 2018. So the model produced by StyleGANs they're capable of generating very high quality photorealistic images, right? So these pictures that you see here, these people do not exist. They are image data produced by StyleGAN. So here in StyleGAN, we have features of one item or image being imposed on another image. So the original video here is that of the horse, right? The zebra is obviously a GAN. These are realistic neural talking head models. So this is one of my favorites. I put a link to the paper. You can check it out later. Maybe because I like Mona Lisa with an attitude. So I put a link to the paper. You can read more on the research. You can read more on it. Big and small companies are already pushing GANs to production, right? So either it's a standalone application on its own or a feature to their already existing products. So if you've used Snapchat filter feature or Face app to make yourself look younger or older, most likely you are using a GAN feature, a feature powered by GANs. So it's either if you are transposing images, you are lifting your face and placing it on another person's body and that sort of thing. Product from Embody Me. It's called the Xpression Camera. So it gives you sort of a virtual makeover, right? So let's say you want to have an online meeting and you don't feel like dressing up on your PJs. You can have this sort of a virtual makeover, like a virtual body, right? And the Ryu is wearing a pajamas and all, and the virtual you is dressed up corporately and that sort of thing. It's very interesting use of GANs. So this is another project called Dualify and was built by I think Jason Antic. I hope I pronounce his surname correctly. So what the project does that uses GANs to color and restore old images and videos, right? So if you have very old videos or very old images that are black and white pictures, black and white images, you can color them, or you can turn them to colored images using GAN. Another favorite product I like from NVIDIA was built using GANs. I'll just play the video for you shortly.
Researchers just invented something amazing that basically replaces a video codec with a neural network which reduces bandwidth consumption by orders of magnitude. We call it AI video compression. With more than 10 million video streams estimated to be live at any given time, video conferencing is the new connectivity challenge for many. Let me show you how it works. The mechanism behind AI-assisted video calls is simple. A sender first transmits a reference image of the caller, just like today's systems that typically use a compressed video stream. Then, rather than sending a fat stream of pixel-packed images, it sends data on the locations of key facial points around the caller's eyes, nose, and mouth. A Generative Adversarial Network, or GAN, on the receiver side then uses the initial image and the key points to reconstruct the subsequent images. As a result, much less data is sent over the network. Slow internet connection and limited bandwidth will not impact the quality of video meetings anymore. Let's take a look at this side-by-side comparison. H.264 compression standard on the left, and NVIDIA AI video compression on the right. Besides the bandwidth consumption, you can see the obvious visual quality as well, by providing significant cost savings for data transfers in the cloud. Reducing bandwidth consumption significantly improves the video conferencing experience for end users, who can enjoy more features while streaming less data on their local devices. This provides a better experience for video communications with AI, so even people who only have access to extremely low bandwidth can still upgrade from voice to video calls. The technique works even when callers are wearing a mask, headphones, hat, or even glasses. By automatically adjusting the position of a caller's face, it's easier to make eye contact. It eliminates the common problem of callers who seem to be looking off the screen or need to stare at a camera above their monitor to appear to be looking at you directly.
And NVIDIA is at the forefront of this revolution.
We can also use the same method for character animations.
Using different key points from the original video, we can output to different styles, including clothing, hair, or even animated game characters.
Video conferencing is going through a renaissance, and we're excited users worldwide, no matter of their video connection, will have a better video call experience because of AI.
If you have the time, I'd like you to look at other papers on generative adversarial networks. Also, TensorFlow has great tutorials on GANs as well. Thank you for your time. Any questions?